Hey everyone, welcome to the discussion section for CS 109 at Stanford. This is week 4, which makes this our third discussion section together. Today, we're going to be talking a bit about continuous random variables and working through this sheet that we have. So before we dive right in, I just want to be clear on continuous random variables. So continuous random variables. We talked about random variables last week, so we should have an understanding of discrete, right? If I have a continuous random variable, then it can assume like any values, right, in this number line. But it takes a discrete number of things, right? So this could go off into infinity, right? But notice that there are like sort of these individual pegs, and each of them has a probability associated with them, right? Um, so if I were to draw this, right, um, you know, it could taper off, and there are infinite number of them, but there are countably infinite amount of them. Whereas in the continuous case, right, I have a distribution that could look, like that. And if it looks something like that, then how I interpret the results of this graph actually change. So in this case, um, if I wanted to assess like what is the probability that x equals 0, I would just say, okay, well, I'm sorry, x equals 1, for example. So this is 1, that's 2. And I would just say, well, it's that bar, right? That's what this tells me. In this other case, it's a little bit more complicated than that. This graph, if I try to assess the probability x equals 1, um, I'm always going to have 0 probability, which you might ask, why is that? Since it touches the graph somewhere, right? And um, uh, stepping back on the kinds of problems we're asking, if you ask, what is the probability x equals 1 in a continuous case, and this was say time, right? This was like seconds, like, how many seconds will have elapsed after some amount, right? Or like with the exponential variable, right? Time until the next event, right? That's what it represents. Well, if you say x equals 1, what's the probability of that? It is a infinitesimally small thing for it to be exactly 1.0000000, right? Infinitesimally small. And so what we say is that this graph does not represent the probability. This actually represents the rate probabilities accumulate. And since it represents the rate probabilities accumulate, right, then interpreting very much about what this number means isn't going to actually help me answer probability questions in many cases. What is going to help me is when I integrate over a bound. So if I say, what is the probability that, it's in some interval between 1 and 2, well, that's an answer that I can get to by integrating over that. And we're familiar with integration because we've taken calculus. So these are the kinds of questions that you would ask of a continuous distribution, because with a continuous distribution, you're always talking about domains, right? And you're talking about all these possible range of values that could be on an interval. Okay. By the way, we talked a bit about the sample space, and I'm not going to spend too long on this, but like we talked a bit, about how like in the discrete case, you've got like a finite number of things. This is the sample space, and the random variable is just a function, and it maps these items to the number line, right? Well, in the continuous case, it's a bit more complicated because there's an uncountably infinite number of items, right? And so what it ends up happening is you have to use a little bit more sophisticated math, what's called measure theory. So almost measuring like the volume of sets. This is way beyond the scope of the course, and there's no need to get into the details of this, but I encourage you to look at it after the exam, presumably, if you're interested more into it. Okay, great. So let's jump into these problems. Any questions about that, about continuous distributions? This is, again, the rate probabilities accumulate. That's what this graph represents. It does not represent a probability itself. You get a probability, you have to integrate to get an actual probability. Okay, doesn't look like there are any questions. And by the way, I can't see the chat. It's not as accessible. Let me pull it up. So jumping in and interrupting me is a great thing uh, to get my attention. Okay, so, oh shoot. Um, okay. All right. So this first one is you have a website where only one visitor can be on the site at a time, but there's an infinite queue of visitors. Immediately after a visitor leaves, a new visitor comes. On average, visitors leave your website after 5 minutes. On average, it says. Assume the length of stay is exponentially distributed. What is the probability that a user stays more than 10 minutes if we calculate this probability? Okay, so this first one with x, we're just saying x is distributed as an exponential, right? Uh, and its graph is going to look something like this, right? Going to look something like that. And basically, we can ask about the intervals, right? Like, what is the probability that the time until the next event is on this interval, right? That's basically what this is getting at. So in this case, using the random variable x, okay, so A is asking about it as an exponential, and B is actually asking about Poisson, which we'll get to in a moment. And there it turns out that there's a relationship between these two kinds of random variables. So what is the probability that the user stays more than 10 minutes? Okay, so first of all, for this exponential, does anyone know what we should put for lambda, which is our parameter of this exponential? This lambda should be the rate, right? The number of events per unit of time, right? Does anybody have any ideas about what to make this?
1/5?
One fifth. Okay, and how'd you get that?
Because I was thinking of it as rate. So in every 5 minutes, there's on average one person who leaves.
Great. So let's clarify this actually. What's really nice about exponential variables is you can actually be somewhat flexible with how you define your unit of time, right? So let's say a unit of time is 1 minute, right? Well, if it's 1 minute, right, then we could ask the question, in that unit of time of 1 minute, how many events do we expect? And since we say we only expect one every 5 minutes, well, then this rate will be 1/5, right? Because we would only expect a fifth of an event every 1 minute, right? On average, that kind of thing. Obviously, you can't observe a fractional amount of events, but we say on average, right? This is a rate. So defining it this way, what we're going to ask is, okay, what is the probability x is greater than 10? Okay. And it turns out that we could actually just ask what is the probability that x, 1 minus the probability that x is less than or equal to 10, right? This would be easier to grapple with. And by the way, with a continuous random variable, it doesn't matter if you have less than or equal to, because since whether I'm including this infinitesimal sliver or not doesn't actually affect my computation. At least it wouldn't in any scenario that I'm familiar with. So don't quote me on that in terms of the theory. But in terms of the practical use cases of this class, it shouldn't ever be an issue. So both of these could be greater than equal to. Both of them could be I'm just saying that sign doesn't matter too much for us. That's all I'm saying. In terms of more in-depth theory, don't worry too much about why. Okay, so so now that we have this, we can just say, well, that's just going to be 1 minus. We can use this capital F of x of 10, right? This capital F of x is the cumulative distribution function, right? If you remember, it's just the integral from negative infinity up to that point of that distribution. But in this case, where the support of this random variable is just from 0. So it's really just the integral from 0 to it, right? But if you look on Google or Wikipedia or anything, you could find what the equation for this is. And it actually just turns out to be 1 minus e to the negative lambda times our input, which is 10, right? And so that's going to be e to the negative 2, which is going to be approximately 0.1353. Okay. So one thing to notice about this is I said at the top that we can be very flexible with how we define our parameter for lambda. And in this case, the lambda we said represents a rate of 1/5 per unit of time, and our unit of time was 1 minute, right? But if we kept our rate at say, let's say that we made the rate 10 minutes, right? If rate was 10 minutes, right? Well, then what would lambda be?
110.
Nope. It would actually be 2. It would
Oh.
actually be 2. And the reason is because the problem says that we expect one event every 5 minutes. And so we would expect 2 events every 10 minutes, right? That's why lambda would be 2. Does that make sense? So that we have this lambda equals 2, right? And we could frame the problem that way. But if we made that our unit of time interval, then we would have to say probability of x is greater than 1, because our unit of time interval is 10 minutes, right? Our unit of time interval is 10 minutes. And we're asking, okay, over that one interval, right, which we defined as 10 minutes, over that one interval, what is the probability that x is greater than that, right? And you notice, if you notice, the math would still exactly work out because the lambda would increase by this factor, right, of whatever it increases by, and then the 10 would it would increase by a factor of 10, and this number would decrease, right? Like this would increase, that would decrease by a factor of 10, right? And we get the same answer. We still get this 2 here. Does that make sense? So you can be flexible with this exponential about how you define your rate. Okay, let's jump to this next one. So any questions on that? I gotta move a little quickly. All right, and then for this next one, it's asking about a Poisson. So with the Poisson, we actually need to be more restrictive about the interval because the Poisson says number of events in a specific unit of time, right? And so we have to define a unit of time is 10 minutes. Like we have to do that, right? And then we say, what is the probability that we don't see any in that unit of time, right? So in this case, right, we're going to have y is distributed as a Poisson with lambda equal to, right? Similar to what we saw before with the exponential when we define that as our interval, right? But now we're asking a different query. We're saying, what is the probability y equals 0? Because this distribution is mapping something different, right? We're saying like, we've got a probability there and a probability there and a probability there, whatever. And then we're saying, what is the probability we didn't see any events in that interval? Well, that's just grabbing that bar, right? So it's asking a somewhat different question, right? And because of that, we can evaluate this by just plugging into the probability mass function, right? And we're going to have 2 to the 0, e to the negative 2 over, over 0 factorial. And that's just going to be e to the negative 2, which should look familiar because that's just 0.153. Okay, I'm going to fly through this next one. We basically have this distribution. I'm sorry, we have this density function. And this density function basically looks a certain kind of way, right? So let's say that we have some function, right? And we choose an arbitrary interval. It doesn't really matter what the interval is. We chose 0 between 0 and 1 is where it's defined. But pay no mind to that. That was has nothing to do with probability being between 0 and 1 or anything. We could have chosen like this as the interval from -7 to, I don't know, +9, right? Like that could have been our interval. And all we're saying is, hey, this is a distribution. That's what we're saying. This is a distribution. But it has a degree of freedom where it could be like kind of steeper like that, right? Or it could not. And we're saying what degree of freedom, right, would be compatible with it being a proper probability distribution, right? And to answer that question, we have to just remember that the property that a distribution must have is that it must equal 1 when integrated over on its support. And then in this case, we have this support of between 0 and 1. So we're just going to say, well, normally it's negative infinity to infinity, f of x dx equals 1. But in this case, the support is just from 0 to 1, right? So we're just going to have 0 to 1 of c of e x minus 1, x minus 1, plus e to the negative x dx, right? And if you actually do this integration, right, you'll end up with 1 equals c times e to the 1 minus 1, e to the negative 1, minus e to the 0 minus 1, minus e to the negative 0. That's what you'll end up with. And then you'll end up with the following. You'll end up with 1 over c equals, when you solve for c, 1 over 2 minus 2 over e, right? This is what you'll end up with. And I'll sort of, I'll finish with this. Sorry to go a bit over time. This number turns out to be like 0.79. And just to give you sort of a graphical illustration of what this is supposed to be, this is actually, I have pulled up an online graphing calculator. And can everyone see my graphing calculator? Everyone? Okay. All we're doing is we're saying, hey, on this bound from 0 to 1, this is a distribution. So like what should C be, right? So that this part integrates to 1. That's all we're doing. And it turns out 0.79 is the correct one, approximately 0.79. All right, I'm going to stop the recording now. Thank you guys for attending.